Okay, powers and roots. So we've seen how to multiply complex numbers in rectangular form. We've multiplied complex numbers in exponential form as well. So z is 1 plus I root 3, w is minus 2i. Rewrite both in exponential forms with their principal arguments. Well, so sorry about that. So z is this, w is that. What is useful, again, is knowing the 30, 60, 90 triangle, right? So pi over 3 is the big angle, pi over 6 is the small angle, right angle here, length of 1, short side is 1/2, long side is root 3 over 2, and then the 45, 45, 90 triangle. Two angles are pi over 4 and pi over 4. Right angle here, this is 1 over the square root of 2, and this is 1 over the square root of 2. And they show up a lot because when we do these examples, it's easier to use these triangles than any others. So if z is 1 plus I root 3, root 3 is up here. So, right, root 3, 1, this should be length 2, because if I take this triangle and multiply everything by 2, I get a height of root 3 and a base of 1. So z should be 2e to the I pi over 3. Minus 2i, so 1, 2, 1, 2 is out there. So this is also, this is pi over 3, right? Same lengths, right? 2 and 2 for x and y, so that means we're dealing with a 45, 45, 90 triangle, except this is 2 and this is 2. So if we take the 1 over root 2 and multiply the whole thing, right? If we multiply this entire triangle by 2 root 2, we will get a length of 2 root 2 and side lengths of 2. So w is 2 root 2 times e, and now we have to be careful because we define what our principal arguments are between minus pi and pi. This is minus 3 pi over 4. So there's our z and w. So what's z times w? It'll be multiply the radiuses together, 4 root 2, and then e to the I, add the powers, pi over 3 minus 3 pi over 4. And you have to do a little work to do that subtraction, but not a whole lot. It becomes minus 5 pi over 12. Right, and minus 5 pi over 12 is, well, we take minus 3 pi over 4, subtract off pi over 3, 5 pi over 12 would be about here. So there's z times w. What's w divided by z is, well, now we divide the moduli of the two numbers. So 2 root 2 divided by 2 is root 2. And then we subtract, so we get I pi over 3 minus 3 pi over 4, which is plus 3 pi over 4 minus minus, which is 13 pi over 4. So I'm going to give myself a little more space here. See if I can push that down to the next page. Okay. So we've got root 2 e to the I 13 pi over 4. But where is 13 pi over 4? Well, 12 pi over 4 is Did we really get 13 pi over 4? Yeah, 13 pi over 12. Sorry, that's why I was confused. There should be 13 pi over 12. Square root of 2 e to the I 13 pi over 12. There we go. Because the common denominator will be 12 and you get 4 plus 9. Okay, so 13 pi over 12 is a little bit more than pi, right? And so pi is this angle. So 13 pi over 12 is a little bit more than that. But we don't allow our principal arguments to be bigger than pi, right? We're only interested in between minus pi and pi. So instead of calling it 13 pi over 12, we're actually going to go this way and say that this is minus 11 pi over 12. Right? So 12 pi over 12 gets you 180 degrees. If you go one more 12 further, you get 13 pi over 12, but that means just going 11 pi over 12 negative. So written with the principal argument, it becomes that. Oh, that's an E. Okay, so you have to be a little bit careful when adding and multiplying and dividing, because you might change the argument might leave the principal argument range, and so you might have to recalculate. Usually we're not going to be hugely picky about principal arguments though, but it is a thing to keep in mind. So what's z to the 10th? Well, we have 1 plus I root 3, which is 2 e to the I pi over 3. So how do you find z to the 10th? Well, trying to find z to the 10th with the rectangular form would just be kind of gross, because you'd have to find the 10th row of Pascal's triangle. But z to the 10th, we can do this as 2e to the I pi over 3 raised to the 10th power. And as long as we're raising it to a nice integer or rational number, we don't run into any problems. One of the things we did in the in-class assignment was showing if this is actually a, if the power is irrational or complex, you can run into some difficulties. So what do we get? 2 to the 10th, e to the I 10 pi over 3. Right, and 2 to the 10th we know is 1024. 10 pi over 3 is the same thing as 4 pi over 3, because you can just subtract off a 2 pi. And to put in its principal argument, that will be minus 2 pi over 3. And so what are the actual rectangular coordinates of this? Well, minus 2 pi over 3, how do we draw that? Well, minus pi over 3 is 180 degrees, so to get to minus 2 pi over 3, you draw, there's 1 pi over 3, and then there's 2 pi over 3s, and then a minus 3 pi over 3 gets you out here. So if you've got a denominator of 3, you say, okay, 1, 2, 3 angles to go. So if this is minus 2 pi over 3, then this angle here is pi over 3. That means this angle is pi over 6. So this triangle here is my 30, 60, 90 triangle. So what point did we actually end up at? E to the minus I 2 pi over 3 has x coordinate, let's see, this is the short half, minus 1/2, and that's the long half, minus root 3 over 2. So that point is minus 1/2, minus root 3 over 2. So what is this point here in rectangular coordinates? It's minus 1/2 minus I root 3 over 2, because the cosine of 2 pi over 3 is minus 1/2 of minus 2 pi over 3 is minus 1/2. The sine of minus 2 pi over 3 is minus root 3 over 2. And if you distribute your 1024 in, you get that. So using exponential forms makes calculating powers pretty easily. We can do the same thing to do trig identities. We know e to the I t equals cosine t plus I sine t, which means e to the I t squared is cosine t plus I sine t quantity squared. This is e to the I 2t, right? Because you multiply the 2 down there. And this is, now if we square this out, this will become cosine squared t, right? Cosine times cosine, and then we get a cosine times I sine t and another cosine times I sine t for the inner and outer terms. That's times an I, and then we get a minus sine squared t, because when we square this term, we get an I squared sine squared, so minus. This thing, though, is cosine of 2t plus I sine of 2t. And this whole thing, if I collect the terms, it's cosine squared minus sine squared plus I times 2 cosine t sine t. So cosine 2t is cosine squared minus sine squared. Sine 2t is 2 cosine t sine t, which are trig identities that you've seen before. So equality of complex numbers is easy in rectangular form, right? A plus IB equals C plus ID means that A equals C and B equals D. Exponential form, R to the I theta equals SE to the I phi means that the moduli R and S are the same, but the powers, right, theta and phi, those angles, theta minus phi is a multiple of 2 pi, right? Theta and phi differ by 2 pi, which includes 0, of course, right? Because 0 is a multiple of 2 pi. So we found that z equals 1 plus I root 3, and that's 2e to the I pi over 3. So z is 2e to the I pi over 3. Find all square roots, basically, of z. So if we take w equals se to the I phi, then w squared will be se to the I phi quantity squared, which is s squared e to the I 2 phi. So if we want this to be equal to 2e to the I pi over 3, what does that mean? S squared has to equal 2. And 2 phi has to be pi over 3 plus 2 pi k, where k is some integer. And note that this, right, is just some number that's in the argument of z. So what does that tell us? Well, s is square root of 2, so that's not too hard, right? And we always want s to be positive because it's modulus. It's the modulus of w, so it's got to be positive. So what does phi have to be if we try and solve this for phi? So phi could be, right, if we take this equation and we just divide it by 2, phi could be pi over 6. That's what we get when we take k equals 0. Phi could be pi over 6 plus pi. That's where we take k equals 1. Phi could be pi over 6 plus 2 pi, right? If we take k equal to 2. Phi could be pi over 6 plus 3 pi, pi over 6 plus 4 pi, etc. Right, so if I take 2 pi and divide it by 2, I get pi. If I take 4 pi and divide it by 2, I get 2 pi. If I take 6 pi and divide it by 2, I get 3 pi. Or it could be pi over 6 minus pi, pi over 6 minus 2 pi, pi over 6 minus 3 pi, etc. So that's all the possible values that phi could be. That's arg phi there. So keep in mind, cosine and sine are periodic with period 2 pi. That means this and this, if I plug them into cosine and sine, will give me the same numbers. And so will that. And so will that. So all the things that are circled, those, if you plug them into this formula, right, and you plug those angles in for phi, you'll get the same number out. So one possibility is W equals root 2 e to the I pi over 6. Okay. The other option is, well, this one. I'll make that a box. But that differs by 2 pi from this one. Right? So those two numbers will give me the same number if I plug them into sine and cosine. And that differs by 2 pi from this one. And that differs by 2 pi from that one. So all these values of phi would give me the same value for W. So root 2 e. Now we have to be careful. This is 7 pi over 6, which is not allowable as a argument. Pi over 6 minus pi is minus 5 pi over 6. So that would be my principal argument. So there's two values for W. Those are my two square roots. Okay. Now if I represent these geometrically, what are they? Well, Z is at an angle up here. It's at distance 2, so this distance is 2, and the angle is pi over 3. This W is, we've cut the angle in half, and the length now is root 2. It's the square root of this, and the angle is pi over 6. The other angle is directly opposite it, and it's also root 2. And so this is root 2 minus 5 pi over 6. And these two angles, this one and this one, that's pi, so these are diametrically opposed to them. So when I get two square roots, right, they're actually diametrically opposed to each other across the origin, and they have the same length. So a nice geometric representation of that. What about higher roots? What are all the fifth roots? I'll give myself a little space here. What are all the fifth roots of minus 1 plus I? Minus 1 plus I, so out there, right? Modulus of Z is the real part squared plus the imaginary part squared. So that's 2. So the modulus of Z equals square root of 2. Okay, what's theta or T? This angle, well, this is a 45-degree angle here, so it's pi over 4, 2 pi over 4, 3 pi over 4. So Z equals root 2 e to the I 3 pi over 4. So what are all the fifth roots? Well, we'll set W equal to S e to the I phi. And we get the same thing that we had before. S to the fifth has to equal root 2. That tells me that S equals, well, fifth root of the square root is actually the 10th root of 2, which is a number very close to 1. Phi, well, 5 phi, if we raise this to the 5, has to be in the argument of Z. So this has to be either 3 pi over 4 or 3 pi over 4 plus 2 pi or 3 pi over 4 plus 4 pi, or 3 pi over 4 plus 5 pi. No, not 5 pi, 6 pi. And I'm going to have to go along for a while to 8 pi, and then to 10 pi, and then to 12 pi. I need a bunch of them because I foolishly made this very, doing the 5th power. Okay, so 5 phi has to be one of those. Okay, so what does that mean that phi can be? Phi can be 3 pi over 20, or, because you divide by 5, divide this by 5 would be 3 pi over 20 plus 2 pi over 5, right? And that's what, 8 pi over 20? Right? So if I take the 2 pi, divide it by 5, put it in the common denominator with the 3 pi, 8 pi over 20. 3 pi over 20 plus, now we take the 4 pi over 5, multiply top and bottom, we get 16 pi over 20. And you can start seeing the pattern. We're just going up by an 8 pi over 20 each time. 24 pi over 20. That would be my, let's see, my 6 pi over 5, multiply top and bottom by 4. The 8 pi would be 3 pi over 20 plus 32 pi over 20. And then the 10 pi would be 3 pi over 20 plus 10 pi over 5 times 4 on top and bottom, 40 pi over 20. And then we get 3 pi over 20 plus 48 pi over 20. And then, there's a whole bunch of others. So how many of these actually give us different numbers when we plug them into sine and cosine? This, 2, 3, 4, 5, but that's 2 pi. So this whole thing gives me the same value as that. This whole thing is 2 pi plus 8 pi over 20. So that would give me the same value as that. So now I've just started repeating. So I actually have 5 values. 2, 3, 4, 5 values of my phi. So what are my possible W's? 10th root of 2 times e to the I 3 pi over 20. 10th root of 2, 11 pi over 20, 10. 3 pi over 20 plus 16 pi over 20 is 19 pi over 20. Three pi over 20 plus 24 pi over 20 is 27 pi over 20, but 27 pi over 20 goes past pi, so we can't use it as a principal argument. If you go the other way, though, 27 pi over 20 is going to be minus 13. That's a 10. E minus I 13 pi over 20. And then the last one is 35 pi over 20, which is root 10 e to the minus 5 pi over 20. So there's all my roots. Great, so how are they distributed? Well, I'll put in a circle whose radius is the 10th root of 2, because all of these numbers have the same root. 3 pi over 20, well, you break the circle up into 40 angles. 3 pi over 20 is here, and then we go up 8 pi over 20 to 11 pi over 20, which will be about here. And this distance is 8 pi over 20, so we go up by that much. And then we go another 8 pi over 20 to get to 19 pi over 20. And then we go another 8 pi over 20 to get to minus 13 pi over 20, and then down to that. So they're equally spaced around the circle. There's 5 of them, and they're equally spaced around that circle. How do we find the first angle? You take the angle of the original, right, which was 3 pi over 4, and you divide that by 5. Right? So 3 pi over 4 over 5 divided by 5 gives me this, and then we just go around by 8 pi over 20. What are the 10th roots of z equals 1? So how many roots of 1 are there? 1 is, you can write it as e times I to the 0, e times I to the 0, e times I to the 2 pi, e times I to the 4 pi, dot, 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 dot. 10th roots, we can get up to e to the I 20 pi. So if we take the 10th roots of this, we're just going to divide each of these angles by 10. And so we're left with e to the I 0, e to the I pi over 5, e to the I 2 pi over 5, dot, 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 all the way down to e to the I 19 pi over 5. What will be 19 pi over 5? 10 pi over 5. Sorry, 9 pi over 5. 2 pi divided by 10 is pi over 5. 20 pi divided by 10 would be, 2 pi. Yeah, e to the I 19 pi over 5. And then e to the I 20 pi over 5. Oh, sorry. E to the I 9 pi over 5. Then e to the I 10 pi over 5, which is e to the I 2 pi, which just brings us back here. So what are the 10 roots of z? Well, we take the circle, what are the 10 roots of 1? We take the circle and divide it up into 10 angles. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And there are my 10 roots of 1. So every number that's not 0, will have 10 roots, 10 tenth roots, 100 hundredth roots, etc., etc.